Calculus BC, we are looking at section 3.7, a section with incredible ties to physics, and chances are you will be doing these types of problems in your physics classes as well. Let's say that you have a position particle. You have a particle that's moving. By the way, this is going to also be what we call rectilinear motion. Rectilinear motion actually means that we are traveling in a line. We're traveling in a horizontal line or a vertical line. And S of t would be a position, and if it's a horizontal movement, your horizontal position would be an x value on the x-axis, really. But we're a function with respect to time. Take a look here. Number one, velocity, v of t, is the derivative of your position function. Now, position, of course, can be positive or negative. Velocity can be positive or negative. We're going to talk about what that means very soon. Number two, speed. If we're going to talk in general about speed, speed is the absolute value of velocity. Let's just say that your velocity is -3 miles per hour. Well, your speed, of course, would be +3 miles per hour. Speed is what we call a scalar. It's always positive. Velocity is a vector. That sign issue, positive, negative signs, indicate direction. So velocity will indicate a quantity, but also a direction. So speed's the absolute value of velocity. Number three, acceleration. A of t is the derivative of v, or the second derivative of your position function. And for number four, the particle travels to the right or up, if this is a vertical motion problem, but the particle will travel right or up if your velocity is positive. Likewise, your particle will travel left or down if velocity is negative. So, in other words, if you have a velocity of -3 feet per second, that's really your change in position. It's like saying that you're losing 3 feet per second, and that's always going to indicate in a horizontal component traveling to the left. One last thing, and this is important, Roman numeral 5 here. A particle is speeding up when velocity and acceleration have the same sign. They're either both positive or both negative. And a particle is slowing down when velocity and acceleration have opposite signs. Okay? I think what can puzzle kids sometimes is, the issue about velocity and acceleration having the same sign being negative. Think about that just for a second. Let's talk about that. Let's just say that your velocity was -3 feet per second. It's negative. Let's say that your acceleration, the way velocity is changing, let's say it's -1 feet per second every second. So it's -1 feet per second squared. And sometimes kids look at this and they'll say, you're telling me that you're speeding up. Yes. Look, this right here, -3 feet per second, that means that you're traveling to the left. Imagine that you're traveling to the left 3 feet per second. But how are we changing with our velocity? That's what a derivative really is. It's a rate of change. How velocity is changing with respect to time. You could say, well, look, every second now, you would have a -1 feet per second every second. So think about it this way. If you start with -3 feet per second, and then if you lose another -1 feet per second, you'd be at -4 feet per second, wouldn't you? You're still traveling to the left, but you're actually then traveling faster, aren't you? So that's where velocity and acceleration could both be negative. I think that's so important for us to talk about. Having the same sign means that either velocity and acceleration are both positive or they're both negative. Likewise, if you have opposite signs, you're going to be working against each other, so to speak. The end result will be to slow down. So let's take a look at some problems together. For example 1, it says, given the horizontal position s of t equals negative 2t cubed plus 15t squared minus 24t minus 6 on this interval, this is really saying that t is only between 0 and 5, right? When is your particle traveling to the right? Well, let's take a derivative. V, we'd get negative 6t squared. Bring down the 2 here, we'd have a 30t. And then the derivative of negative 24t is just going to be negative 24. And you could say, okay, so when are we traveling to the right? Well, if you were looking right back up here with the fourth little part of the notes, you're traveling to the right when velocity is positive. And it's good to find out when velocity is 0. That, of course, means that your particle would be at rest, wouldn't it? Your particle actually would come to a stop. Let's just solve here. If I were to factor out a negative 6, we'd have t squared minus 5t, and if we divided out a negative 6 here, I guess that'd be a plus 4, wouldn't it? Hey, we can look at that. That's, kind of nice. And then what? Well, we could do some factoring still. We could say, well, let's factor that down to t minus 4 and t minus 1. And you'd say, where does that equal 0? Well, that would equal 0 when t minus 4 could equal 0, or t minus 1 could equal 0, and that'd be t equals 4 and t equals 1. So that's where we are stopped. That's where we're going to be at rest. But I'm going to make a little number line right here, and maybe this is a cool thing to take a look at. Remember, I'm on the interval from 0 to 5, so here's a 1 and here's a 4, and you'd say, well, the 1 and the 4, I hope, are pretty evident why I'm putting that on the number line. The 0 and the 5, well, we're just between those, and we could real quickly just say, well, ultimately, I'm interested in what's happening with velocity. Look, if I may, I could real quickly say we could test t equals 1/2 between 0 and 1. Between 1 and 4, we could maybe test t equals, say, a 2. Between 4 and 5, we could test, say, t equals 4. And of course, kids are going to say, test what exactly? Well, look, your v is negative 6 times t minus 4 times t minus 1, right? So here we go. If I were to plug in a 1/2 in here, I think it's pretty evident that all three parts of this factoring would be negative. 1/2 minus 4 is something negative. 1/2 minus 1 is something negative, and the negative 6 is out there. A negative times a negative times a negative is a negative. So v is negative there. We're going to be traveling to the left. And then what? Well, we could say, well, what about if I plugged in a 2? Well, you could see that this last parenthesis would be positive, but your other ones would be negative. And a negative times a negative is a positive, and a positive right there multiplied in. You can see, hey, look at this. We're going to be traveling to the right then. Finally, if you plug in, I meant to say plugging in like a 4.5, testing a 4.5 between 4 and 5. You can see that your two parentheses here are both going to be positive, but you've got a negative out in front. So you can see via the number line that velocity is positive between 1 and 4. So to answer the question, we are traveling right you're going to be traveling to the right on the interval from 1 to 4. Or, if you wanted to use an inequality, you do it that way. So, hey, that's a wonderful start. Let's then also take a look at answering the second part here. When is the particle speeding up? Well, if we come back to the very last part of the notes right here, starting us off, you're speeding up when velocity and acceleration have the same sign. You know what you actually need to do is talk about the acceleration. Look, if I may, I'm going to highlight the velocity right here. That's your velocity function. So what's your acceleration function going to look like? Well, your acceleration function is going to look like this. Take your derivative. You get negative 12t plus a 30. And that's great. Sometimes that's all you'll be asked to do for a problem. But tell you what, if I'm interested in the sign of acceleration, I'd like to set it equal to 0. And I'm going to add a 12t over here. I'm going to divide by a 12. And 30 divided by 12, well, I can divide out a 6 out of both of those, and we'd get 5 over 2, or 2.5. Well, look, if I may, I could go ahead and say here's 0, and here's a 5, and here's your acceleration. And here's your 5/2, or 2.5. Let's test some values and just see what we get. If I plug in a 1 right up in here, negative 12 times 1 is negative 12 plus 30. That's going to be something positive. And then what? If I plugged in a 3, negative 12 times 3 is negative 36 plus 30. That would be something negative. Now, I am most interested in where these two quantities of velocity and acceleration have the same sign. So you may superimpose the graphs. Look, I'm going to recopy the velocity curve. But right above it, I'm going to have acceleration. So the big question is, and you know, in between the 1 and the 4 here, I guess I just really want to tell you it's all positive, isn't it? You're going to ask yourself, where do velocity and acceleration both have the same sign? Well, you know, they're both positive between 1 and 2.5, right? But there's a second part to this, and that's between 4 and 5. Velocity and acceleration have the same sign. Everywhere else, acceleration and velocity will have opposite signs, right? And when you've got the opposite signs, you're actually slowing down, right? So we're going to be speeding up between a 1 and a 2.5. And also between 4 and 5. So the reason for that is because acceleration and velocity would have the same sign. Let's real quickly take a look at vertical position. Vertical position so very often is given by this formula that you see right here. Let's just take a quick look at that. G, if we are in feet, is the gravitational constant so Earth pulls an object down towards itself at negative 32 feet per second every second. So if an object is dropped, acceleration is how velocity changes. You can see this is really what is happening. Every second, another 32 feet per second pointed in that downward direction is attributed to its velocity. It picks up speed in absolute value, so to speak, but your velocity becomes more and more negative. You can see you keep dropping negative 32 feet per second every second. So an object is fired straight up with this beginning velocity, that's v naught right here, 20 feet above the ground. That's your initial position. So write an equation for s. Let's see if we can do that real quickly. S of t would be your g, which is negative 32, t squared all over 2. What's your beginning velocity? Well, that's 500, isn't it? And then what's your beginning position? That's 20. And real quickly, you're going to be able to get this position function. This is only for what we call projectile motion, when something is launched upwards or dropped. We really just have vertical motion. Honestly, your motion is in a straight vertical line. They want us to find the time and the velocity when this object hits the ground. And, to find the time when that will occur, you're going to say, well, I want my position 0, s to equal 0 right here. And now at this point, wow, we just have to go ahead and solve that. There are many different ways you can solve this. You can solve it with for sure with the quadratic formula. That would definitely be one way that you can do that. And if you have the quadratic formula built into your calculator, that's wonderful. I, of course, would like to show you something a little bit different. I'd like to point out that you could be using your calculator. Let's just say that you've got negative 16x squared plus 500x plus 20. And you know that's a parabola that opens down, right? And graphing this, well, if you were to graph in a window, you definitely wouldn't want to have a zoom standard being the view to help you see what's happening right here, right? I think as soon as you hit trace, you can see that you're up at 20, and then it's going to be going way up. You can see that we're up around 2,000 something. Oh my goodness, as you're looking at that, and it looks like it's continuing to go up quite a bit. As we're beginning to try to move this down a little bit, you could say, well, what if I changed up here even to go, say, to 3,000, and maybe that's not enough. If we just hit graph right there, you can begin to see, looks like I haven't even gotten to the vertex of that parabola just yet. Right now I'm just doing some guessing and checking. What if we did 25 and it just did 5? Just trying to show you real quickly. It's beginning to look a little bit better. You can begin to see that if we just make this go a little bit higher, maybe have this go up to 4,000 maybe, and make our scale out here, maybe go to 35. Let's see what happens here. Pretty soon you can see that things are looking pretty good. You can begin to see that right now you have where your parabola is going to be touching 0. Look, you could just as well make this negative 1,000. And maybe this looks a little bit better. Your y-intercept is at 20, but I guess what I'm trying to see right here is, can I find where the parabola is touching down? Yeah, of course you can. If we went to second calculate, if we go to 0, the 0 is the x-intercept. One of the requirements of using the graphing calculator in an AP Calculus class is being able to find zeros of a function. Hit enter when you're to the left of it. Hopefully you've done this